the most powerful eye humanity has ever built, just shattered everything we thought we knew about existence. James Webb Space Telescope peered 13.5 billion years into the past and found something that should be impossible. Galaxies containing hundreds of billions of stars existed just 400 million years after the Big Bang. Our physics says they cannot exist. They are too massive, too ancient, too perfectly formed. Yet there they are, burning in the darkness of deep time, defying every equation we wrote. Scientists are now scrambling to rewrite the fundamental rules of cosmic evolution. The universe is not only older than we calculated, it is stranger, vaster, and more mysterious than anyone imagined. If you want to see what the most advanced telescope in history revealed about reality, hit that like button and subscribe. Now, get yourself comfortable. Let's begin. The first images from James Webb Space Telescope arrived on Earth in July 2022. Scientists expected beauty. They expected clarity. They expected to see further than ever before. What they did not expect was to find their fundamental understanding of cosmic evolution shattered within weeks of the telescope opening its golden eye. Deep within those initial images lurked galaxies that should not exist. Massive spiral structures containing hundreds of billions of stars appeared in regions of space so ancient that light from them had travelled for over 13 billion years. These galaxies existed when the universe was barely 400 million years old, a cosmic infant by any reasonable measure. The scientific community had spent decades preparing for Webb's launch. Engineers folded 18 hexagonal mirror segments into a configuration that would survive the violence of rocket launch. Technicians tested every component against the extreme cold of deep space. Mission planners calculated orbital trajectories to position the telescope at the second Lagrange point, 1.5 million kilometers from Earth, where the gravitational influences of the Sun and Earth create a stable orbital pocket. The total investment exceeded $10 billion and consumed 25 years of development. All of this preparation aimed at one goal, seeing deeper into cosmic history than any instrument had seen before. Nobody prepared for what that deeper vision would reveal. To understand why this discovery terrifies and excites astronomers in equal measure, you must first grasp how galaxies are supposed to form. Standard cosmological models describe a slow, deliberate process spanning billions of years. After the Big Bang, matter distributed itself almost perfectly evenly through expanding space. The universe began as a nearly uniform soup of hydrogen and helium, with density variations so small they measured barely 1 part in 100,000. These tiny variations, quantum fluctuations stretched to cosmic scales during the first fraction of a second of existence, created regions where matter was slightly denser than average. Gravity went to work on these dense patches with patient persistence. Over hundreds of millions of years, matter fell inward toward the densest concentrations. First came small clumps containing perhaps 1 million solar masses. Then larger structures accumulated as clumps merged together. Dwarf galaxies formed first, containing only millions of stars scattered through dark matter halos, spanning thousands of light years. These cosmic building blocks merged over billions of years, gradually assembling the massive spiral galaxies we see today. Our own Milky Way required approximately 10 billion years of merger activity to reach its current size of 400 billion stars. The process resembled construction more than explosion. Small pieces combined into medium pieces. Medium pieces combined into large structures. Large structures continued growing through ongoing mergers and gas accretion. The models describing this process were elegant. The mathematics worked beautifully. Computer simulations running on the world's most powerful supercomputers produced virtual galaxies that matched observations across cosmic time. Every major telescope confirmed the predictions. Hubble Space Telescope observed galaxies at various distances, corresponding to various ages, and the size progression matched theoretical expectations. Galaxy formation appeared to be a solved problem, understood in sufficient detail that astronomers could predict what Webb would find. They predicted that the earliest galaxies would appear small, irregular, and primitive. Clumps of gas just beginning to form their first stars. Blue smudges marking the locations where cosmic structure was only starting to emerge from primordial uniformity. The first 500 million years of cosmic history should show a universe still assembling itself, not a universe already filled with mature galactic structures. Then James Webb looked deeper than any instrument had looked before, and everything changed. The telescope designated Glass Z13 became the first sign of trouble. This galaxy appeared in Webb's initial deep field observations, captured during the telescope's first weeks of scientific operations. Light from Glass Z13 had travelled for approximately 13.4 billion years before entering Webb's golden mirrors. When astronomers calculated its mass using standard techniques that had worked reliably for decades, the numbers made no sense. Glass Z13 contained billions of stars packed into a structure that had formed within 300 million years of the Big Bang. Not millions of stars, like the primitive dwarf galaxies models predicted. Billions. An entire galactic population assembled in a time frame that should have allowed for nothing more than initial gravitational collapse. 300 million years. Consider what this time frame means in cosmic context. The universe itself is approximately 13.8 billion years old. 300 million years represents barely 2% of cosmic history. In human terms, this is like a newborn baby appearing fully grown and running marathons within the first week of life. The developmental stages that should precede maturity simply did not occur. The galaxy appeared in its mature form almost immediately after the universe began. But Glass Z13 was just the beginning. As Webb continued observations throughout 2022 and 2023, more impossible galaxies emerged from the darkness of deep time. Each new discovery pushed the boundaries of what physics supposedly allowed. The galaxy cluster, called Abell 2744, provided some of the most dramatic revelations. This massive foreground cluster sits approximately 3.5 billion light-years from Earth, containing thousands of galaxies bound together by gravity. Webb used Abell 2744 as a gravitational lens, exploiting Einstein's prediction that mass bends the fabric of space-time itself. The cluster's enormous gravity, equivalent to several quadrillion solar masses, warped space-time so severely that light from background galaxies curved around the cluster like water flowing around a stone. This gravitational lensing magnified background galaxies by factors of 10 or more, revealing structures that would otherwise remain invisible even to Webb's powerful instruments. The cluster acted as a cosmic telescope, extending Webb's already unprecedented reach even further into the ancient universe. Behind Abell 2744, astronomers found galaxies that existed when the universe was merely 3% of its current age. These were not primitive collections of gas and dust struggling to form their first stars. They were not the small, irregular smudges that models predicted. They were fully developed structures with complex morphologies, containing stellar populations that implied generations of previous evolution. One galaxy designated JADES GSZ 130 contained approximately 400 million stars crammed into an area smaller than our Milky Way's central bulge. Its stellar population showed signs of multiple generations of star formation, meaning that stars had formed, lived their entire lives, died in supernova explosions, and seeded new stellar generations with heavy elements. All of this cosmic cycling had occurred within 400 million years. The timeline barely allowed for a single massive star to complete its life cycle, yet here was evidence of several complete stellar generations. The physics of stellar evolution made this finding particularly disturbing. Stars like our Sun live for approximately 10 billion years, slowly fusing hydrogen into helium in their cores. but massive stars burn through their fuel much faster. These stellar giants live fast and die spectacularly, exploding as supernovae that scatter heavy elements through surrounding space. For JADESGSZ 13-0 to show evidence of multiple stellar generations, the galaxy must have formed its first stars almost immediately after the Big Bang. Those stars must have lived and died quickly. Their supernova remnants must have enriched surrounding gas with heavy elements. New stars must have formed from this enriched gas, and the cycle must have repeated multiple times, the entire sequence compressed into a window of cosmic time that should have been far too brief. The discovery of what scientists nicknamed the sparkler galaxy added another layer of confusion to an already perplexing situation. This ancient structure appeared surrounded by compact globular clusters, dense balls containing hundreds of thousands of old stars that typically form only in the earliest phases of galactic evolution. Globular clusters in our own Milky Way are among the oldest structures in the galaxy, with ages approaching 13 billion years. But the sparkler's globular clusters showed chemical compositions suggesting they had already experienced multiple enrichment events from stellar explosions. Heavy elements like iron and gold had been forged in supernova detonations and neutron star mergers, then distributed through the clusters, then incorporated into new stars forming from the enriched gas. The chemical complexity implied a history of stellar evolution that should have required billions of years to accumulate. All of this had occurred within a time frame our models said was impossible. The universe simply had not existed long enough for these structures to form through the gradual processes our physics describes. Yet there they were, burning in the darkness of deep time, defying every equation astronomers had written. Scientists initially suspected instrument errors. Perhaps Webb's detectors were misreading the light. Maybe calibration issues created false signals that mimicked ancient galaxies. The instruments were new, after all. Webb had only recently completed its commissioning phase. Strange readings might reflect problems with the telescope rather than problems with the universe. Research teams spent months cross-checking observations. They compared data from different instruments aboard Webb. They analyzed the same targets repeatedly, using different observation strategies. They examined whether dust within our own galaxy might be contaminating the signals. They considered whether active galactic nuclei, supermassive black holes consuming material and radiating intensely, might be mimicking the signatures of massive stellar populations. The ancient giants refused to disappear. Every test confirmed their existence. Every analysis validated the initial findings. The galaxies were exactly where they appeared to be. Exactly as massive as calculations suggested. Exactly as impossible as they seemed. The photometric redshift measurements told a consistent story. Light from these galaxies had stretched during its 13 billion year journey through expanding space, shifting from visible wavelengths deep into the infrared. The amount of stretching directly corresponded to distance and age. More stretching meant more distant, which meant more ancient. Webb's instruments, specifically designed to capture this shifted ancient light, were working perfectly. The near-infrared camera and near-infrared spectrograph detected exactly the signals they were built to detect. The galaxies registered at redshifts exceeding 10, corresponding to cosmic ages less than 500 million years after the Big Bang. Spectroscopic confirmation followed. Instead of relying solely on photometric estimates, which infer redshift from how much light appears in different color filters, astronomers obtained detailed spectra from individual galaxies. These spectral fingerprints revealed the precise chemical compositions of ancient stellar populations. The spectra showed emission lines from hydrogen, oxygen, and other elements at wavelengths that confirmed extreme distances. Hydrogen's characteristic Lyman alpha emission, normally appearing in ultraviolet wavelengths, had redshifted into the infrared precisely as physics predicted for objects at such extreme distances. The impossible galaxies were confirmed as genuinely ancient. No measurement error could explain them away. The implications cascaded through every subfield of astronomy. If massive galaxies could form within the first few 100 million years, then something about our fundamental understanding was wrong. But what exactly had we missed? Dark matter provides the gravitational scaffolding where normal matter collects and forms stars. This invisible substance constitutes approximately 85% of all matter in the universe. It does not emit light or interact with electromagnetic radiation, but its gravity shapes cosmic structure at every scale. For galaxies to grow so quickly, dark matter halos must have collapsed faster and formed deeper gravitational wells than simulations predicted. Standard simulations show dark matter halos growing gradually through a process called hierarchical assembly. Small halos form first from the densest primordial fluctuations. These small halos merge into larger halos over cosmic time. The merger process takes billions of years because halos must orbit each other, gradually losing energy through dynamical friction before finally combining. Webb's observations suggest this gradual assembly simply did not happen. The early universe produced massive halos almost immediately, or normal matter found ways to accumulate in halos far more efficiently than models assume, or both. Either way, the standard picture of structure formation requires revision. Alternatively, star formation itself might work differently than astronomers believed. Standard models assume that gas converts into stars at relatively modest rates, limited by feedback processes that blow material away from star-forming regions. When massive stars form, their intense radiation heats surrounding gas, preventing it from collapsing into new stars. When those massive stars explode as supernovae, the explosions drive powerful shock waves that push gas away from star-forming regions. This feedback keeps star formation inefficient. In typical galaxies today, only about 1% of available gas converts into stars during any given orbital period around the galactic center. The gas persists, recycling through multiple generations of star formation over billions of years. But the Webb galaxies suggest that early star formation was far more efficient, converting available gas into stars at rates 10 or 20 times higher than local galaxies manage today. Perhaps the first stars formed so quickly that feedback processes could not develop in time to regulate the runaway collapse. Perhaps the absence of heavy elements in primordial gas changed the physics of stellar birth in ways our models do not capture. Some researchers proposed even more radical solutions. Perhaps the first stars were fundamentally different from stars that form today. These population 3 stars, theorized but never directly observed, would have formed from pure hydrogen and helium without any heavy elements. The absence of metals changes everything about stellar physics. In modern molecular clouds, heavy elements like carbon and oxygen help gas cool efficiently. As gas cools, it can collapse to higher densities without generating enough pressure to halt the collapse. This cooling allows modern stars to fragment into relatively small masses, producing stars ranging from 1/10 to perhaps 100 solar masses. Without metals, primordial gas could not cool as efficiently. Higher temperatures generated higher pressures that resisted fragmentation. Instead of breaking into many small clumps, primordial clouds may have collapsed into single massive objects. Population: 3 stars might have reached hundreds of solar masses, perhaps even 1,000 solar masses. These stellar behemoths would have burned through their nuclear fuel in merely 2 million years, a cosmic eye blink, before exploding as hypernovae that enrich surrounding gas for subsequent stellar generations. But even population 3 scenarios struggle to fully explain Webb's observations. The sheer number of ancient massive galaxies poses statistical problems that simple stellar physics cannot resolve. If such rapid galaxy formation represents a rare fluke requiring exceptional initial conditions, we should not expect to find so many examples in relatively small survey areas. Webb observes only tiny patches of sky with its deepest observations. The Hubble ultra-deep field covered approximately 11 square arc-minutes, roughly 1/13 millionth of the total sky. Webb's deep fields cover similarly small areas, yet every deep Webb observation seems to uncover new candidates for impossibly ancient massive galaxies. The phenomenon is not rare. It appears to be common, which means it cannot be explained by statistical fluctuations or exceptional circumstances. The crisis deepened when astronomers compared Webb observations to predictions from the lambda cold dark matter model. Lambda CDM represents the standard framework for understanding cosmic structure. The lambda refers to the cosmological constant, Einstein's term for the energy density of empty space that drives accelerating cosmic expansion. Cold dark matter describes the invisible gravitational scaffolding that shapes structure formation. Lambda CDM successfully explains the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space with faint microwave light. It explains the distribution of galaxies on large scales, the cosmic web of filaments and voids. It explains the accelerating expansion driven by dark energy. For 3 decades, this model has passed every observational test thrown at it with flying colours. Webb's ancient galaxies represent the first clear evidence that lambda CDM might be incomplete. The model predicts a specific timeline for structure formation. Dark matter halos grow gradually through mergers. Galaxies within those halos assemble through hierarchical build-up. Large structures form late, emerging from the merger of smaller precursors over billions of years. Webb shows that the universe did not follow this script. The universe wrote its own narrative, one where massive structures appeared almost immediately after cosmic time began. Whatever process drove this rapid assembly operated with an efficiency that lambda CDM does not predict and current physics struggles to explain. Research teams have proposed modifications to lambda CDM that might accommodate Webb's discoveries. Some suggest that dark matter might interact with itself through previously unknown forces, causing faster clumping in the early universe. Self-interacting dark matter would allow halos to collapse more rapidly by providing additional friction that speeds up the merger process. Others propose that primordial black holes, formed from density fluctuations during cosmic inflation, seeded early galaxy formation by providing gravitational anchors where matter accumulated quickly. If the universe contained numerous black holes with masses ranging from hundreds to thousands of solar masses before the first stars formed, these objects could have served as nucleation points around which matter rapidly collected. Still, other researchers question whether the standard cosmological parameters are precisely correct. The Hubble constant, which measures the expansion rate of space, remains contentiously measured. Different methods yield different values that disagree by nearly 10%. Local measurements using supernovae and Cepheid variable stars give higher expansion rates. Measurements derived from the cosmic microwave background give lower rates. This Hubble tension might indicate that our understanding of cosmic expansion is fundamentally flawed. If the universe expanded differently than current models assume, the timeline for structure formation would shift accordingly. Perhaps the universe is older than 13.8 billion years, providing more time for massive galaxies to form. An older universe would give gravity more time to work, potentially resolving the tension between observed structures and theoretical predictions. Each proposed solution creates new problems while solving old ones. Modifying dark matter properties affects predictions for galaxy rotation curves and gravitational lensing that lambda CDM currently explains well. Primordial black holes face constraints from observations that limit how many could exist without producing other detectable effects. Alternative expansion histories must reconcile with precise measurements of the cosmic microwave background that strongly constrain cosmological parameters. No single modification has yet emerged that satisfies all constraints while explaining Webb's impossible galaxies. The scientific community finds itself in a rare position. For the first time in decades, major astronomical observations directly contradict well-established theoretical predictions. This is not a minor discrepancy that clever modelling might resolve. This is a fundamental challenge to our understanding of how structure formed in the early universe. Some astronomers embrace this crisis as an opportunity. Genuine contradictions between theory and observation drive scientific progress. The history of astronomy is filled with moments when unexpected discoveries forced complete revisions of accepted models. Galileo's observations of Jupiter's moons contradicted geocentric cosmology and ultimately overturned the Earth-centered model of the universe. Hubble's discovery that galaxies are receding from us in all directions overturned the static universe model and revealed cosmic expansion. Perhaps Webb's ancient galaxies herald another such paradigm shift. Others urge caution, noting that Webb has operated for only a short time. More observations are needed. More sophisticated analyses must be performed. The history of astronomy also contains examples of exciting discoveries that faded with additional scrutiny. Claims of faster-than-light neutrinos evaporated when measurement errors were identified. Reports of cosmic inflation evidence in the cosmic microwave background were later attributed to galactic dust. Extraordinary claims require extraordinary evidence, and the claim that standard cosmology is fundamentally wrong certainly qualifies as extraordinary. But as Webb continues observing, as data accumulates, as independent analyses confirm and reconfirm the findings, the extraordinary evidence is mounting. What remains certain is that James Webb Space Telescope has revealed a universe that does not match our expectations. The cosmos generated massive, complex structures far earlier than any model predicted. Whatever process drove this rapid assembly operated with an efficiency that current physics struggles to explain. The universe proved more creative, more energetic, and more capable of rapid organization than we imagined. Standing in the light of these impossible galaxies, humanity confronts a humbling reality. Our sophisticated models, built from decades of observations and refined through countless computer simulations, apparently missed something fundamental. The equations that seem to describe cosmic evolution with precision and elegance turn out to be incomplete at best, possibly wrong at their foundations. The ancient giants discovered by Webb force us to reconsider everything we thought we understood about cosmic evolution. They suggest that the early universe was not a primitive realm of slowly condensing gas, but a dynamic environment where tremendous structures assembled with shocking speed. They hint that the processes governing galaxy formation remain poorly understood despite half a century of intensive study by thousands of dedicated researchers. But perhaps the most profound implication concerns not the past, but the future of scientific understanding. If our models failed to predict what Webb would find, what else might we have wrong? What other aspects of cosmic evolution might contradict our careful theories? Webb has only begun its observations. Each new deep field might reveal additional surprises that challenge established knowledge. The telescope is scheduled to operate for at least 20 years, possibly longer if its systems continue functioning. During that time, it will observe thousands of ancient galaxies, mapping the early universe with unprecedented detail. Each observation adds to our understanding while potentially deepening the mystery. The more we learn, the more we realize how much remains unknown. The impossible galaxies represent more than astronomical curiosities. They stand as monuments to scientific humility, reminders that the universe remains far stranger than our models suggest. They demonstrate that even our most successful theories merely approximate a reality of far greater complexity. They show that nature repeatedly surprises those who study it, overturning confident predictions with observations that nobody anticipated. And they promise that the most powerful telescope ever built will continue revealing truths that reshape human understanding of cosmic existence. The universe keeps secrets that even our best instruments are only beginning to uncover. Webb has opened a window onto an ancient cosmos that defies our expectations. What we see through that window will change everything we think we know about how the universe became what it is today. The first images shattered assumptions. The subsequent observations deepened the mystery. The implications continue cascading through astronomy, cosmology, and physics. And somewhere in the darkness of deep time, impossible galaxies burn with light that has traveled 13 billion years to tell us that our understanding of cosmic reality is far less complete than we imagined. Light is a time machine. This fact sounds poetic, but operates through straightforward physics that governs everything we observe about the cosmos. Photons travel at precisely 299,792 kilometers per second through the vacuum of space. Nothing travels faster. Not rockets, not radio signals, not information of any kind. This cosmic speed limit represents the fundamental barrier that defines what we can know about the universe and when we can know it. This speed limit means that light from distant objects requires time to reach observers. When you look at a star 100 light-years away, you see that star as it existed 100 years ago. The photons entering your eyes departed from that stellar surface when your great-grandparents were children. The star might have changed dramatically since then. It might have expanded into a red giant. It might have exploded as a supernova. You would not know because the light carrying that information has not yet arrived. The same principle applies across all cosmic distances. When astronomers observe the Andromeda Galaxy, 2.5 million light-years away, they see it as it existed when early humans first began crafting stone tools in Africa. The light carries ancient information across space, delivering messages from the past directly to telescopic mirrors. Every observation of the distant universe is simultaneously an observation of the ancient universe. James Webb Space Telescope exploits this principle to an extreme never before achieved. From its orbital position described earlier, the telescope maintains the extreme cold necessary for its mission. Instruments approach temperatures of -233 degrees Celsius, cold enough that the telescope's own heat does not contaminate the faint signals arriving from billions of light-years away. This thermal control is essential because Webb observes primarily in infrared wavelengths. The infrared focus is critical because of what cosmic expansion does to ancient light. As photons travel through expanding space over billions of years, their wavelengths stretch. Short wavelengths become longer. Blue shifts toward red. Red shifts into infrared. For the most ancient light in the universe, this cosmological redshift becomes extreme. Photons that left primordial galaxies as visible light arrive at Earth as infrared radiation, wavelengths too long for human eyes to detect. Previous telescopes like Hubble operated primarily in visible and near-infrared wavelengths. Hubble could detect some redshifted light from ancient sources, but its capabilities fell short of observing the most distant cosmic objects. The most ancient galaxies remained invisible behind their redshifted disguise. They existed in plain sight, their light streaming toward Earth across billions of years. But they could not be seen because their radiation had shifted beyond detection limits. Webb was designed specifically to penetrate this barrier. Its primary mirror, 6.5 meters across and coated in gold, collects infrared light with unprecedented efficiency. Gold reflects infrared wavelengths better than aluminum or other common mirror coatings. Each photon arriving from the distant universe bounces off golden surfaces before reaching instruments calibrated to detect the faintest infrared signals. The instruments themselves operate at temperatures that would freeze any gas instantly. The mid-infrared instrument requires cooling to -266 degrees Celsius, just 7 degrees above absolute zero. At this temperature, thermal noise drops to levels that allow detection of individual photons arriving from sources billions of light-years distant. The engineering required to maintain these temperatures while operating complex electronics represents one of humanity's greatest technical achievements. When Webb observes a galaxy 13 billion light-years away, the light entering its mirrors left that galaxy 13 billion years ago. The telescope does not see the galaxy as it exists today. That galaxy has continued evolving for 13 billion years, since emitting the light we now observe. Stars have formed and died within it. Planets have coalesced from stellar debris. Perhaps civilizations have risen and fallen on worlds orbiting its stars. We know nothing of these subsequent developments because information about them travels at light speed and has not yet reached us. What Webb sees is a cosmic fossil. a snapshot preserved in ancient photons that have travelled nearly the entire age of the universe to reach us. These photons carry information about conditions that existed when the cosmos was less than 1 billion years old. They reveal a universe fundamentally different from the one we inhabit today. Processing this ancient light transforms every deep space observation into an archaeological expedition through cosmic history. The results have revealed the cosmic dawn, that mysterious epoch when the first stars ignited and began transforming the universe from darkness into light. This transition represents the most fundamental transformation in cosmic history since the Big Bang itself. Before the cosmic dawn, the universe contained only darkness. After it, light filled expanding space, and the processes creating everything we observe today had begun. For approximately 380,000 years after the Big Bang, the universe was opaque. This opacity had nothing to do with dust or obscuring clouds. The entire universe existed as plasma, a state of matter where temperatures are so high that electrons cannot remain bound to atomic nuclei. Free electrons filled space so densely that photons could not travel far before scattering off these charged particles. Light was trapped. Photons bounced endlessly through the cosmic fog, unable to travel in straight lines for any significant distance. The universe glowed with thermal radiation, but that radiation could not propagate freely. Every photon scattered countless times, its direction randomized with each encounter. Its information about distant regions scrambled beyond recovery. Then expansion cooled the universe below approximately 3,000 degrees Kelvin. At this threshold temperature, electrons slowed enough to be captured by protons. Neutral hydrogen atoms formed throughout space for the first time. Suddenly the fog cleared. Without free electrons to scatter them, photons were released to travel freely through space. This transition is preserved in the cosmic microwave background radiation, the oldest light we can detect. The cosmic microwave background represents the surface of last scattering, the moment when photons throughout the universe began their unimpeded journeys through space. These photons have been travelling for 13.8 billion years, stretching from their original visible wavelengths into the microwave portion of the electromagnetic spectrum as space expanded. But the universe after recombination was dark. No stars had yet formed. No galaxies illuminated the cosmic void. Hydrogen gas drifted through expanding space, gradually condensing under gravity's patient influence. Dark matter halos collapsed first, creating gravitational wells where normal matter would eventually accumulate. But the process took time. For perhaps 100 million years, the universe contained no luminous sources. This period is called the Cosmic Dark Ages. It represents a chapter of cosmic history that no electromagnetic observation can directly reveal. During the Dark Ages, no electromagnetic radiation was being produced. The cosmic microwave background continued streaming through space, but it carried only information about conditions at recombination, not about the darkness that followed. The Dark Ages were not empty of activity. Gravity worked continuously, pulling matter toward dense regions, building the scaffolding where galaxies would eventually form. Dark matter halos grew through mergers. Gas flowed along filaments toward nodes, where concentrations would become significant. The cosmic web that shapes all subsequent structure was taking form. But none of this produced light. Then came first light. Somewhere in the darkness, a cloud of primordial hydrogen collapsed under its own gravity. The cloud compressed, heating as gravitational potential energy converted to thermal motion. Pressure increased as density grew. At the cloud's center, temperatures eventually reached 10 million degrees Kelvin. At this threshold, hydrogen nuclei moved fast enough to overcome their electrostatic repulsion and fuse together. Nuclear fusion ignited. The first star in cosmic history began to shine. This moment represents one of the most significant transitions in the history of the universe. For hundreds of millions of years, the cosmos had contained only darkness. Now a point of light burned where none had existed before. Shortly afterward, perhaps within the same collapsing region, other stars followed. Dense clouds fragmented into multiple cores, each igniting in succession. These pioneering suns generated ultraviolet radiation far more intense than anything in the modern universe. Without heavy elements to absorb and re-emit energy efficiently, these primordial stars burned hotter than any subsequent stellar generation. Their surfaces reached temperatures exceeding 50,000 degrees Kelvin, compared to our Sun's 5,800-degree surface. This intense radiation began ionizing the surrounding neutral hydrogen, stripping electrons from atoms and creating bubbles of plasma in the neutral medium. These bubbles of transparent space carved through the opaque intergalactic medium like flashlight beams through fog. Photons could travel freely within these ionized bubbles, though they were absorbed when encountering the neutral gas beyond. This epoch of reionization marks the boundary between darkness and light in cosmic history. It did not happen instantaneously. Different regions ionized at different times depending on when luminous sources formed within them. The process took several 100 million years to complete, with bubbles growing around each source and gradually merging until the entire intergalactic medium became ionized. Webb was designed to observe this transition, to witness the universe waking from its primordial sleep. And the telescope has delivered observations that reveal this epoch with unprecedented clarity. Each deep field image captures galaxies at various stages of the reionization process. Some appear embedded in neutral hydrogen, their radiation still struggling to clear the surrounding darkness. Others have carved extensive clear zones, their bubbles beginning to merge with neighboring sources. The spectrum of ancient light carries information about what that light encountered during its journey. When photons pass through neutral hydrogen, specific wavelengths are absorbed. Hydrogen atoms absorb photons at characteristic frequencies corresponding to electronic transitions. The most prominent absorption occurs at the Lyman alpha wavelength, where photons have exactly the energy needed to boost hydrogen electrons from their ground state to the first excited state. This absorption creates distinctive features in observed spectra. Gaps appear where certain wavelengths should exist but do not. The light was absorbed during transit through neutral hydrogen somewhere along the line of sight. By analyzing these absorption patterns, astronomers can determine how much neutral hydrogen existed at various distances corresponding to various cosmic epochs. Webb's spectroscopic observations of ancient galaxies revealed that reionization was not a uniform process. Some regions of space cleared of neutral hydrogen earlier than others. Galaxies in dense environments, where star formation began earliest, created ionized zones that expanded rapidly. Galaxies in sparse regions remained embedded in neutral hydrogen for longer periods, their radiation struggling to clear the surrounding medium. Bubbles of ionized gas expanded around the first luminous sources at rates determined by the intensity of ionizing radiation and the density of surrounding gas. More luminous galaxies created larger bubbles. Denser environments required more photons to ionize. The overlapping bubbles gradually merged until the entire universe became transparent, completing the transition roughly 1 billion years after the Big Bang. The observations suggest that galaxies provided most of the ionizing radiation rather than individual stars scattered through intergalactic space. Collections of young, hot stars pumping out ultraviolet photons created the overlapping ionization bubbles that eventually filled all of intergalactic space. Dwarf galaxies, too faint for previous telescopes to detect, may have contributed significantly to this cosmic transformation. Webb caught several galaxies in the act of ionizing their surroundings. These cosmic pioneers appeared as brilliant blue points surrounded by extended halos of emission where their radiation interacted with nearby neutral gas. The halos glow with Lyman alpha emission, produced when ionized hydrogen recombines and the resulting atoms cascade through energy levels. The shapes of these ionization regions revealed how photons propagated outward from galactic sources, illuminating the surrounding darkness 1 light-year at a time. The morphologies of these ionization bubbles provided constraints on the properties of early stellar populations. Rounder bubbles suggested steady radiation output from stable stellar populations. Irregular bubbles indicated variable sources, perhaps galaxies with episodic star formation, or active galactic nuclei flickering on and off. The bubble structures preserve records of conditions that no longer exist, frozen in the patterns of ionization they created. But Webb saw deeper still. The telescope detected candidate galaxies at redshifts exceeding 14, corresponding to cosmic ages less than 300 million years after the Big Bang. At these extreme distances, light is stretched by factors exceeding 15. Radiation that left ancient galaxies as visible light arrives at Webb as thermal infrared, deep in the wavelength regime, where only Webb's cooling allows detection. If confirmed through detailed spectroscopy, these objects would represent the earliest stellar structures ever observed. They hover at the very edge of what the universe could plausibly produce in such limited time. Their existence pushes against the constraints imposed by the finite age of the cosmos and the finite speed at which physical processes can operate. The physical conditions in these primordial environments differ dramatically from anything in the modern universe. Gas contained only hydrogen, helium, and trace amounts of lithium, the elements produced in Big Bang nucleosynthesis. No heavier elements existed because no stars had yet lived and died to create them through nuclear fusion and explosive dispersal. Webb detected signatures of this primordial chemistry in the spectra of ancient galaxies. The ratio of different elements revealed how much enrichment had occurred from previous stellar generations. Some galaxies showed near-pristine compositions, suggesting their stars formed from gas little different from the original Big Bang mixture. Others displayed surprising metal enrichment, indicating that rapid stellar evolution had already processed material through multiple generations of massive stars and supernova explosions. The stellar populations within these ancient galaxies matched theoretical predictions for the population 3 stars discussed in the previous section. Spectral features suggested higher temperatures, more extreme ultraviolet outputs, and masses exceeding typical modern stellar populations. These massive primordial stars would have burned through their nuclear fuel in merely millions of years, seeding surrounding gas with heavy elements necessary for subsequent stellar generations and rocky planet formation. Webb also revealed the structures of ancient galaxies in unprecedented detail. Previous telescopes showed primordial systems as fuzzy blobs, collections of light without discernible features. The limited resolution and sensitivity of earlier instruments smeared ancient galaxies into featureless smudges. Webb's resolution and infrared sensitivity transformed these blobs into recognizable structures with internal complexity. Spiral arms appeared in galaxies existing when the universe was just 1 billion years old. These organized structures require specific conditions to form. Rotating disk structures must develop from infalling gas that retains angular momentum. Density wave perturbations must propagate through the stellar medium, creating compression regions where gas concentrates and star formation intensifies. Such features were thought to require billions of years of settled evolution. Webb showed that galactic architecture could emerge remarkably quickly. Central bulges distinguished from surrounding disks in many ancient systems. Bars appeared, elongated structures that channel gas toward galactic centers. The structural diversity of the ancient universe resembled the modern cosmos far more than theoretical expectations suggested. The telescope also detected active galactic nuclei in the ancient universe. Supermassive black holes actively accreting material and producing tremendous radiation. Some of these black holes contain masses exceeding 1 billion solar masses, existing when the universe was less than 1 billion years old. Growing such massive black holes in such brief cosmic intervals poses severe theoretical challenges. Standard black hole formation begins with stellar collapse. When massive stars exhaust their nuclear fuel, their cores collapse to form black holes of perhaps 10 or 20 solar masses. These stellar mass black holes grow by accreting surrounding material. but growth is limited by radiation pressure from the accretion process itself. Material falls inward toward the black hole, forming a swirling accretion disk. Gravitational energy converts to heat. As material spirals closer, the disk glows intensely, producing radiation across the electromagnetic spectrum. This radiation pushes against inflowing material, creating an outward pressure that limits how fast new material can fall in. At maximum efficiency, called the Eddington limit, a black hole might double its mass every 40 million years, starting from a 10 solar mass stellar remnant. Growing to 1 billion solar masses would require roughly 1 billion years of continuous feeding at this maximum rate. The black hole would need to accrete without interruption for longer than the universe had existed when Webb observed these ancient monsters. Either these black holes started with much larger seed masses, perhaps from the direct collapse of primordial gas clouds rather than stellar evolution, or they grew through super-Eddington accretion at rates exceeding theoretical limits, or our understanding of black hole physics requires fundamental revision. Each possibility carries profound implications for cosmic evolution. Direct collapse black holes represent one theoretical solution. Under specific conditions, primordial gas clouds might collapse directly into black holes with masses of 10,000 to 100,000 solar masses without first forming stars. This requires suppressing molecular hydrogen cooling to prevent fragmentation. Intense ultraviolet radiation from nearby sources could provide this suppression, destroying molecular hydrogen and allowing monolithic collapse. If direct collapse black holes formed in the early universe, they would provide much more massive seeds for subsequent growth. Starting from 100,000 solar masses instead of 10 solar masses changes the timeline dramatically. The same Eddington limited growth that seemed impossible becomes merely challenging. The presence of supermassive black holes in ancient galaxies also affects how those galaxies evolved. Active galactic nuclei produce powerful jets and radiation that can heat surrounding gas, shutting down star formation by preventing gas from cooling and collapsing. Alternatively, jets might compress gas clouds and trigger enhanced star formation. This feedback relationship between black holes and their host galaxies apparently began operating almost immediately in cosmic history. Webb's observations of the cosmic dawn have revealed an epoch of furious activity where stars, galaxies, and black holes all raced to form as quickly as physical processes allowed. The universe at 300 to 700 million years old was not the primitive realm of slowly condensing hydrogen that models predicted. It was already a complex environment, with sophisticated structures that had somehow assembled with shocking speed. Looking backward through time to this cosmic dawn, Webb sees a universe in rapid transition. The Dark Ages ended as the first luminous sources ignited. Ionizing radiation carved expanding bubbles through neutral hydrogen, merging into the transparent universe we observe today. Heavy elements began accumulating in regions where stars lived and died, seeding subsequent generations with the materials for rocky planets. Galaxies assembled from merging components, growing through hierarchical processes that operated faster than anyone expected. Black holes grew at mysterious rates that challenge our understanding of accretion physics. All of this cosmic activity compressed into a time frame that seems impossibly brief. The universe transformed from primordial simplicity to cosmic complexity in perhaps 500 million years. Changes that should have required billions of years occurred in mere fractions of cosmic history. Webb reveals this transformation with every deep field image, each observation adding constraints on what processes drove early structure formation. Standing at the temporal edge of observable existence, James Webb Space Telescope has become humanity's window on creation itself. The light entering its golden mirrors carries information from epochs when the universe was fundamentally different from the cosmos we inhabit today. Processing this ancient light reveals not just what the early universe looked like, but how physical processes operated under conditions that will never return. The cosmic dawn that Webb observes happened everywhere in the universe simultaneously. The first stars ignited throughout expanding space, not in one special location but in countless regions where conditions permitted collapse and fusion. We observe specific examples of this universal process, because light from those particular locations happened to travel toward Earth across the intervening billions of years. But identical transformations occurred in every direction, at every distance, filling the cosmos with light over a span of several 100 million years. The cosmic dawn represents a phase transition that swept through the entire universe, converting darkness to light everywhere at once. This universality means that Webb's observations reveal not just isolated curiosities but fundamental cosmic processes, the physics driving early star formation applied everywhere in the universe. The mechanisms assembling ancient galaxies operated universally. The conditions enabling rapid black hole growth existed throughout the young cosmos. Webb provides specific examples of universal transformations that shaped everything we observe today. The edge of time visible to James Webb Space Telescope represents the fundamental limit of electromagnetic observation. Beyond the cosmic dawn lies the Dark Ages, when no light was produced. Beyond that lies the opaque plasma era, when light could not propagate. No telescope operating at any wavelength can peer further back through conventional observation. The cosmic microwave background forms an absolute horizon, a wall of light from the moment space first became transparent. This wall surrounds us in every direction, marking the boundary beyond which electromagnetic observation cannot reach. Yet Webb approaches this wall more closely than any previous instrument. Its observations of galaxies and structures less than 300 million years after the Big Bang sample cosmic conditions just emerging from the Dark Ages. The universe in these observations had barely transitioned from opacity to transparency. The cosmic fog had only recently cleared. The first light was still spreading through space. To see this epoch is to witness the universe becoming itself. Before this moment, the cosmos contained potential but not form. After this moment, structures began emerging that would eventually produce everything we observe today. The galaxies Webb detects at extreme redshifts are ancestors to the galaxies we see nearby. Some of those planets would develop conditions suitable for life. The chain connecting those ancient observations to human existence stretches across 13 billion years of cosmic evolution. But Webb lets us see how that chain began, observing the first links being forged in the cosmic dawn at the very edge of time. The universe is not a random scattering of galaxies through empty space. This assumption guided early astronomical thinking for centuries. Astronomers catalogued individual galaxies, measured their distances, plotted their positions on charts. The distribution appeared haphazard, cosmic objects scattered like salt grains thrown across a dark tablecloth. Nothing suggested underlying organization beyond what gravity produced through random clustering. This picture was fundamentally wrong. Underlying all visible structure lies an invisible framework that shapes cosmic organization across scales, stretching billions of light years. This scaffolding, composed primarily of dark matter, determines where galaxies form, how they cluster, and what patterns emerge when astronomers survey the cosmos at the largest scales. Without understanding this hidden architecture, observing galaxies is like studying leaves while remaining ignorant of the trees and forests they compose. James Webb Space Telescope has revealed this hidden architecture in unprecedented detail. The telescope's observations show that the cosmic web extends further and contains more complexity than any previous observation suggested. What appeared as scattered individual objects now reveals itself as an interconnected network of staggering intricacy. The true scale of cosmic organization dwarfs not just individual galaxies, but entire galaxy clusters, stretching across distances that challenge human comprehension. Dark matter constitutes approximately 85% of all matter in the universe. This substance does not emit light, it does not absorb light, it does not scatter, reflect, or interact with electromagnetic radiation in any detectable way. Dark matter interacts with normal matter only through gravity, the weakest of the four fundamental forces. These properties make dark matter invisible to conventional telescopes that collect electromagnetic radiation. You cannot photograph dark matter. You cannot see it through any telescope ever built. Yet dark matter's gravitational effects are unmistakable. They appear in observations across every cosmic scale, from individual galaxies to the largest structures in the universe. Galaxies rotate faster than their visible matter can explain. The stars and gas orbiting galactic centers move at velocities that should fling them into intergalactic space if only visible matter provided gravitational attraction. Something invisible holds galaxies together. Galaxy clusters bend light from background sources more strongly than their luminous components would allow. When light from distant galaxies passes near a foreground cluster, that light curves around the cluster, following the warped geometry of space-time. The amount of bending indicates the total mass responsible. In every cluster measured, the mass inferred from lensing far exceeds the mass visible in stars and gas. Invisible matter dominates. The cosmic microwave background shows density variations that require far more matter than atoms alone provide. These tiny temperature fluctuations, measured to exquisite precision by satellites like Planck, encode information about the matter content of the early universe. The patterns match predictions only when dark matter is included. Without dark matter, the observed structures simply cannot form. For decades, astronomers mapped dark matter distribution through these indirect methods. They measured how galaxies moved within clusters, inferring total mass from orbital velocities using equations derived from Newton and Einstein. They analyzed gravitational lensing in detail, calculating mass distributions from how space curved around invisible concentrations. They ran computer simulations, growing virtual universes over cosmic time. These simulated universes matched observed galaxy patterns only when dark matter was included in the initial conditions. These techniques revealed that dark matter forms vast halos around individual galaxies. Our own Milky Way sits embedded within a dark matter halo, extending perhaps 300,000 light-years from the galactic center, far beyond the visible disk of stars. This halo contains roughly 10 times more mass than all the stars and gas we can see. We inhabit a small island of luminous matter, floating within an ocean of invisible substance. But dark matter organization extends far beyond individual galaxies. Halos connect through filamentary structures that link galactic systems across cosmic distances. The entire distribution forms what scientists call the cosmic web, a three-dimensional network of interconnected structures that fills the observable universe. Webb transformed dark matter mapping through superior observations of gravitational lensing. This technique exploits one of Einstein's most profound predictions: mass curves spacetime. Light traveling through curved spacetime follows curved paths. When light from distant galaxies passes near massive foreground structures, space itself bends according to general relativity. The light rays curve, distorting images of background galaxies into arcs, and sometimes producing multiple images of the same source. The amount of distortion directly indicates the mass responsible for the bending, regardless of whether that mass emits light. A concentration of pure dark matter bends light just as effectively as an equivalent mass of luminous stars. By measuring distortions in background galaxy images, astronomers can map the total mass distribution, including the invisible components. Previous telescopes observed strong lensing events where distortion was obvious. Spectacular arcs and Einstein rings appeared around massive galaxy clusters, dramatic demonstrations of space-time curvature. These observations confirmed that clusters contain far more mass than their visible components suggest. But strong lensing requires precise alignment between observer, lens, and source. Only a small fraction of background galaxies undergo strong lensing, limiting the technique's mapping capability. Webb's sensitivity extended this capability to weak lensing. Subtle distortions affecting vast numbers of background galaxies. Every galaxy in the distant universe experiences some degree of lensing from intervening matter. The distortions are tiny, stretching galaxy images by perhaps 1 or 2%. Individual measurements cannot distinguish real elongation from the natural variety of galaxy shapes, but statistical analysis across millions of galaxies reveals coherent patterns. Galaxies that happen to lie behind the same foreground mass concentration all experience similar stretching in similar directions. By measuring shapes across enormous samples, astronomers can extract the weak lensing signal from the noise of intrinsic galaxy shapes. The resulting maps reveal dark matter distributions with precision impossible using any other technique. Webb's infrared sensitivity proved crucial for weak lensing analysis. The telescope detects galaxies at extreme distances that previous instruments could not resolve. These distant galaxies provide background sources for lensing measurements across unprecedented volumes of space. The deeper Webb observes, the more background galaxies it detects, and the more precise the weak lensing maps become. What Webb showed was a universe far more structured than simulations predicted. Dark matter filaments stretch across hundreds of millions of light-years, connecting galaxy clusters in a cosmic network that defies simple description. The closest analogies come from biology rather than physics. The filaments resemble neural connections in a brain, branching and rejoining in complex patterns. They resemble mycelium threads in forest soil, spreading through the medium and connecting distant nodes. They resemble blood vessel networks that branch from major arteries to capillaries, distributing resources through three-dimensional space. These filaments are not uniform tubes of constant density. They are complex braided structures with subfilaments, branches, and density variations along their lengths. Some portions appear thick and well-defined, dense concentrations of dark matter that gravitationally dominate their surroundings. Other portions fade into diffuse extensions that barely distinguish themselves from the cosmic average density. The nodes where filaments intersect mark the locations of massive galaxy clusters. These cosmic crossroads represent the densest concentrations of matter in the universe. Thousands of galaxies swarm within each major cluster, bound by the gravitational potential of the dark matter halo that contains them. The clusters sit at the centers of gravitational drainage basins, drawing material from all the connecting filaments. Within these nodes, Webb's infrared capabilities revealed cluster structures with unprecedented clarity. The dark matter distribution within clusters is not smooth, but contains substructure at multiple scales. Smaller halos orbit within larger halos in a hierarchical arrangement, spanning multiple orders of magnitude in scale. Galaxy-scale halos sit within group-scale halos that sit within cluster-scale halos, like nested dolls of dark matter extending from thousands of light-years to millions of light-years. One breakthrough involved observations of the Abell 382 galaxy cluster, a massive structure lying approximately 240 million light-years from Earth. This cluster had been studied for decades using various techniques, its mass estimated from galaxy velocities and X-ray gas temperatures. Webb observations, combined with gravitational lensing analysis, revealed that previous studies had significantly underestimated the cluster's extent. The cluster's dark matter distribution extended far beyond previous estimates. What appeared to be the cluster edge in earlier observations turned out to be merely where the density dropped below detection thresholds of less sensitive instruments. Webb revealed fainter extensions stretching outward in multiple directions. Tendrils of invisible matter reached toward neighboring clusters, bridges of dark matter connecting Abell 382 to adjacent cosmic structures. These connections suggested that Abell 382 forms just one node in a connected network spanning more than 500 million light-years. The cluster is not an isolated object, but an intersection point in the cosmic web. The boundaries between individual clusters blur into continuous structures that cannot be meaningfully separated. This extended dark matter structure contains subhalos, smaller dark matter concentrations embedded within the larger framework. Some subhalos hosted visible galaxies, their baryonic matter having collapsed into stars and gas within the gravitational wells dark matter provided. Others appeared devoid of stars, pure dark matter clumps detectable only through their gravitational effects on surrounding matter. These dark subhalos represent one of the stranger predictions of cold dark matter cosmology. Theory suggests that dark matter collapsed into vast numbers of small halos in the early universe. Many of these halos never accumulated enough gas to form stars. They remain invisible, contributing to the cosmic mass budget without producing any detectable radiation. Webb's lensing observations provided the first systematic census of these ghost halos, confirming their existence and mapping their distribution within larger structures. The distribution of subhalos matched predictions from lambda CDM simulations in some respects. The number of subhalos and their radial distribution within clusters agreed with computer models. This agreement provided confirmation that dark matter models work correctly on certain scales. Whatever dark matter is made of, it behaves in ways that simulations accurately reproduce, at least for structures larger than individual galaxies. Webb also revealed dark matter structures through their effects on background cosmic light. The cosmic infrared background radiation fills all of space with a diffuse glow from all the stars and galaxies throughout cosmic history. Every photon ever emitted by every star that has ever shone contributes to this background. Most of the light comes from galaxies too faint to detect individually, their combined emissions creating a smooth glow across the infrared sky. This background radiation carries faint imprints from intervening matter. Dark matter concentrations gravitationally amplify specific portions of the background, creating subtle brightness variations. Where dark matter is denser, space curves more strongly, and background light is slightly magnified. Where dark matter is less dense, the magnification decreases. These variations create patterns in the cosmic infrared background that map the cosmic web. Analyzing these brightness patterns required processing Webb observations through sophisticated statistical techniques. The signal is extraordinarily faint, buried beneath instrumental noise, foreground contamination from our own galaxy, and the intrinsic variations in the background itself. Only by combining observations across large sky areas and applying carefully calibrated analysis methods could astronomers extract the dark matter signature. The resulting maps show dark matter filaments connecting visible galaxy superclusters across distances exceeding 1 billion light-years. The cosmic web appeared not as isolated threads but as interconnected sheets and walls, three-dimensional structures that fill space rather than merely crossing it. Some filaments appeared as genuine one-dimensional threads. Others resolved into flattened structures resembling membranes stretched between cluster nodes. The largest coherent structures Webb revealed extended across scales that challenged theoretical expectations. Standard cosmology assumes that the universe becomes increasingly smooth when viewed at larger scales. Eventually, the density variations should average out, and the cosmos should appear uniform. The scale at which this homogeneity appears is called the homogeneity scale, typically estimated at several 100 million light-years. Webb observations suggested that coherent structures persist to even larger scales. Filaments, hundreds of millions of light-years long, showed orientation patterns that aligned across distances approaching 1 billion light-years. These alignments should not exist if matter distributed truly randomly across cosmic volumes. The cosmic web might possess organizational principles operating on scales approaching the observable universe itself. The implications for understanding cosmic evolution prove profound. Galaxies do not form in isolation. They assemble within dark matter halos that themselves exist along filaments feeding material toward cluster nodes. The gravitational framework dark matter provides determines where visible structure can develop. Gas flows along these cosmic highways, channeled by dark matter gravity into regions where star formation occurs. Cold gas streams along filaments toward the dense nodes where clusters form. This gas feeds galaxy formation, providing the raw material from which stars coalesce. The galaxy distribution we observe directly reflects the underlying dark matter architecture. Webb traced this connection by observing galaxies at various cosmic epochs. Ancient galaxies appearing in deep field images clustered along protofilaments, dark matter structures that had not yet fully collapsed but were already channeling matter flow. These early filaments appeared less defined than their modern counterparts, their structures still developing as dark matter continued collapsing. Intermediate-age galaxies inhabited more developed filaments with stronger clustering. The structures had grown denser over cosmic time, concentrating matter more effectively. Modern galaxies filled out the mature cosmic web we see in the nearby universe, their distribution tracing the dark matter framework that took billions of years to fully develop. This evolutionary sequence revealed that filament formation preceded galaxy formation. Dark matter collapsed first into elongated structures, driven by initial density fluctuations from the earliest moments after the Big Bang. Normal matter followed the gravitational roadmap dark matter provided. Stars formed where gas accumulated, galaxies assembled where halos grew massive, and clusters emerged where filaments intersected. The cosmic web was not merely where galaxies ended up. It was why galaxies exist, where they do. The distribution of luminous matter across the universe directly reflects the invisible architecture that gravitationally determined where structure could form. Observing galaxies without understanding this framework misses the fundamental cause of the patterns we see. Webb's observations also constrained dark matter properties. Different dark matter models predict different filament characteristics. The standard assumption, called cold dark matter, proposes that dark matter particles move slowly compared to light and interact only through gravity. Cold dark matter produces sharply defined filaments with abundant small-scale substructure. The halos are dense and concentrated, with steep density profiles rising toward their centers. Warm dark matter represents an alternative model where particles move faster, their thermal motions smoothing out small-scale structures. Warm, dark matter produces smoother filaments with fewer clumps. The smallest halos cannot form because particle motions prevent gravitational collapse below certain scales. Self-interacting dark matter proposes that dark matter particles do interact with each other through forces beyond gravity. These interactions would alter halo structures, particularly in their dense cores where particles frequently encounter each other. Self-interacting dark matter could explain certain observed features that cold dark matter struggles to reproduce. The Webb data favored cold dark matter on the scales measured. Filaments showed the clumpy substructure that cold models predict. Subhalos appeared in roughly the numbers expected from computer simulations. The density profiles of halos matched cold, dark matter predictions better than alternatives. Whatever dark matter is made of, it behaves as a cold, collisionless fluid on scales ranging from individual galaxies to the largest observable structures. But tensions remained that Webb's observations could not resolve. This core cusp problem has plagued dark matter research for decades. Observations sometimes show flatter cores, where density remains relatively constant across central regions. Some subhalo populations seemed lower than expected, particularly for the smallest structures that Webb could detect through lensing. This missing satellites problem suggests either that small halos form less efficiently than simulations predict, or that they exist but remain even more invisible than theory suggests. These discrepancies might indicate incomplete understanding of baryonic physics. Normal matter influences dark matter distribution through gravitational interactions. Supernova explosions can inject energy into dark matter halos, pushing material outward and flattening central density cusps. Properly modeling these complex interactions remains challenging, or the discrepancies might hint that dark matter possesses properties beyond the simple cold collisionless model. Perhaps dark matter particles do interact weakly with each other. Perhaps they possess mass distributions different from the simplest assumptions. The tensions Webb revealed ensure that dark matter research will continue pushing toward better understanding. Webb's deep observations of galaxy clusters revealed another aspect of cosmic architecture that connects visible and invisible matter. Between cluster galaxies floats a vast reservoir of hot gas. material that never condensed into stars but remained suspended in the cluster gravitational well. This intra-cluster medium contains more baryonic mass than all the cluster galaxies combined. The gas reaches temperatures exceeding 50 million degrees Kelvin, far hotter than any stellar surface. At these temperatures, atoms are fully ionized, electrons stripped away to create plasma that emits X-ray radiation. Previous X-ray telescopes like Chandra mapped this hot gas in nearby clusters, revealing extended halos of million-degree plasma surrounding galaxy concentrations. Webb added infrared observations that revealed different gas phases invisible to X-ray instruments. Cooler gas, at merely millions of degrees, emits infrared radiation that Webb detects. This gas exists in filaments and clumps within the hot intracluster medium, remnants of material that has not yet been heated to the extreme temperatures dominating cluster cores. This multi-temperature analysis showed that the intracluster medium is far more complex than simple models assumed. Gas does not exist at a single uniform temperature throughout clusters. Instead, multiple phases coexist. From relatively cool material recently accreted from cosmic filaments to extremely hot plasma that has resided in the cluster potential well for billions of years. Gas filaments thread through cluster volumes, connecting galaxies through shared atmospheric extensions. These gaseous bridges channel material between cluster members, creating pathways along which matter flows from galaxy to galaxy. The bridges fueling star formation in some galaxies, while stripping gas from others through ram pressure as galaxies move through the surrounding medium. The gas distribution directly reflected the underlying dark matter framework. Hot plasma concentrated where dark matter is densest, accumulated in the gravitational wells that dark matter provides. Extended gas structures traced filamentary paths where dark matter reaches between halos. The correlation between visible gas and invisible dark matter demonstrated how intimately the two components are connected despite their fundamentally different properties. The quantity of gas detected exceeded predictions based on previous observations. Standard models assumed that cluster evolution over billions of years would heat and disperse most intergalactic gas, feedback from active galactic nuclei, energy injection from supernovae, and simple thermal expansion should have driven much of this gas beyond cluster boundaries. Webb showed that massive gas reservoirs persist in structures older than models expected. Either heating mechanisms operated less efficiently than assumed, allowing gas to remain bound within cluster potentials, or cooling processes replenished hot gas from continued inflows along cosmic Webb filaments. The cluster gas cycle appears more complex than equilibrium models predicted. This gas excess has implications for a major cosmological puzzle. The search for missing baryons has occupied astronomers for decades. Cosmological models derived from the cosmic microwave background indicate that normal matter, atoms and electrons and everything made from them, constitutes approximately 5% of total cosmic contents. This fraction is precisely constrained by the patterns in the primordial radiation, but adding up all the stars, planets, gas clouds and dust that astronomers observe yields only about half the expected normal matter. Roughly half the baryons predicted by cosmological models simply could not be found. They were not in galaxies, not in hot cluster gas, not in cool molecular clouds, not in any form that previous instruments could detect. Webb observations suggested that much of this missing matter hides in filamentary gas beyond galaxy clusters. The warm, hot intergalactic medium fills cosmic Webb filaments at temperatures between 100,000 and 10 million degrees Kelvin. This gas is too cool to emit detectable X-rays and too diffuse to produce visible signatures. It occupies the vast volumes between clusters, spread so thin that conventional detection methods fail. Webb sensitivity allowed statistical detection of this medium through multiple channels. Gravitational lensing revealed mass concentrations along filaments that exceeded what visible galaxies could explain. Subtle absorption features appeared in spectra of background sources when their light passed through filamentary gas. Faint emission contributions to the cosmic infrared background traced the distribution of warm material throughout the cosmic web. If confirmed through additional observations, this discovery would close the book on a decades-old cosmological puzzle. The missing baryons were never truly missing. They were distributed through the cosmic web in forms too diffuse and too cool for previous detection methods. The baryonic content of the universe matches theoretical predictions. We simply lacked instruments sensitive enough to see where most of it resides. The scale of revealed architecture staggers comprehension. Individual galaxies that seemed significant when viewed alone shrink to insignificance within the cosmic web context. Our Milky Way contains 400 billion stars spread across 100,000 light-years. This seems vast by any human measure, yet in the cosmic web context, our galaxy represents a single node in a filament that stretches toward the Virgo cluster, one of roughly 2,000 galaxies in our local supercluster, itself just one concentration among countless others. The structures Webb revealed extend across scales that challenge human cognition. Filaments spanning hundreds of millions of light-years, walls stretching for billions of light-years, voids containing almost nothing across distances that would take light itself hundreds of millions of years to cross. Webb observations traced filament connections across more than 2 billion light-years of cosmic space. The surveyed volume represented only a tiny fraction of the observable universe, limited by the telescope's field of view and observation time constraints. Yet this small sampling revealed structural complexity that required days of supercomputer analysis to map and characterize. Extrapolating these observations to the full observable cosmos suggests a web containing billions of filaments, connecting trillions of cluster nodes, punctuated by enormous voids where matter density drops to near zero. This architecture existed before any conscious mind arose to contemplate it. The cosmic web took form in the first billion years after the Big Bang, and has continued evolving ever since, a structure vaster than any single observer can perceive. Understanding this architecture remains an ongoing challenge. Computer simulations can now reproduce cosmic web structures that match observations in statistical properties. Given the right initial conditions and physical rules, virtual universes grow filaments, clusters, and voids that resemble the real cosmic web. This agreement suggests that our basic understanding of structure formation is correct, but many questions remain unanswered. Why does dark matter clump along filamentary paths rather than in other configurations? The filamentary structure emerges naturally from gravitational collapse of initially smooth matter distributions, but the precise physics determining filament properties remains incompletely understood. What determines filament widths, densities, and intersection geometries? How do baryons trace dark matter flow across billions of light-years, and what processes determine where gas converts into stars versus remaining diffuse? James Webb Space Telescope has revealed the hidden scaffolding of existence. The invisible framework that determines where matter concentrates and how structures form now appears in observations with unprecedented clarity. This architecture predates stars, predates galaxies, predates any physical process that astronomers traditionally study. The cosmic web arose from quantum fluctuations in the first instance after the Big Bang, grew through gravitational amplification across cosmic time, and now shapes the distribution of everything visible in the night sky. Walking through a forest, you might admire individual trees while remaining unaware of the fungal networks connecting root systems beneath your feet. These mycorrhizal networks transfer nutrients between trees, communicate chemical signals across forest distances, and fundamentally shape which trees survive and where forests grow. The visible trees are just the surface manifestation of an invisible underground architecture. Similarly, observing galaxies without understanding the cosmic web misses the fundamental organization shaping what we see. The galaxies are beautiful, certainly, worthy of study and admiration, but they are surface phenomena, the visible manifestations of an underlying structure that determines their existence. Webb has begun revealing the underground network of the cosmos, the dark matter mycelia threading through space, connecting islands of light across voids of unimaginable emptiness. The true scale of the universe revealed by Webb extends beyond individual cosmic objects to encompass the web itself. This interconnected framework represents the largest coherent structure in existence, the skeleton upon which everything visible hangs. Understanding the universe requires understanding this architecture. Webb has shown us its outlines. The details will occupy astronomers for generations to come. The discoveries made by James Webb Space Telescope do not merely add details to existing cosmic understanding. They require fundamental reassessment of models that astronomers spent decades constructing and verifying. The scale of the universe that Webb has revealed exceeds previous estimates by margins that transform our conception of cosmic existence. What humanity thought it knew about the cosmos has proved to be incomplete. The true reality stretches further toward infinity than our models prepared us to accept. This is not a minor correction. This is not the kind of incremental revision that accompanies normal scientific progress. Webb has revealed that our census of cosmic contents was wrong by factors of 10. Our timeline for cosmic evolution was wrong by margins that break our equations. Our understanding of how structures form was wrong in ways that challenge fundamental physics. The telescope, designed to see further than any instrument before, has shown us that further extends far beyond what we imagined. Consider first the numerical implications. Previous estimates suggested the observable universe contained approximately 200 billion galaxies. This figure emerged from decades of careful observation using the Hubble Space Telescope and ground-based instruments. Astronomers counted galaxies in deep-field images, extrapolated to regions too faint for direct detection, applied statistical corrections for what they knew they were missing. The number seemed secure. Webb's superior sensitivity revealed that this estimate missed most of the cosmic population. Faint dwarf galaxies far outnumber the larger systems Hubble could see. These tiny stellar collections contain only millions of stars rather than billions. They emit so little light that previous instruments could not detect them at cosmological distances, but they exist in staggering numbers, scattered throughout the cosmic web like dust particles in a sunbeam. Updated estimates based on Webb observations now suggest at least 2 trillion galaxies populate the observable universe. This represents a 10-fold increase from previous assumptions. The cosmos contains 10 times more galactic structures than astronomers believed just a decade ago. Every calculation based on the old estimates requires revision. Every model of cosmic evolution must accommodate far more structures than previously considered. But even this number underestimates reality when considered across cosmic history. Webb observations indicate that the early universe contained vastly more star-forming systems than current surveys capture. The ancient cosmos teemed with dwarf galaxies that no longer exist as independent structures. Over billions of years, gravity pulled these small systems together. They merged with each other and were absorbed by larger galaxies. Their individual identities erased through gravitational consolidation. The Milky Way itself consumed dozens of smaller galaxies during its growth. Every major galaxy in the universe has a similar history of galactic cannibalism. The large structures we observe today are amalgamations of countless smaller structures that existed in the cosmic past. The total number of galaxies that have ever existed likely exceeds 10 trillion. They have been absorbed into the massive structures that dominate the modern cosmic census. The universe we observe today represents a processed version of a far more numerous ancient population. Each galaxy contains its own stellar population. The average galaxy harbors approximately 100 billion stars, though this figure spans enormous ranges depending on galactic type and size. Dwarf galaxies contain merely millions of stars scattered through small volumes. Giant elliptical galaxies contain trillions of stars packed into massive spheroidal structures. Spiral galaxies like our Milky Way fall somewhere in between, with hundreds of billions of stellar furnaces burning through nuclear fusion. Multiplying galaxy counts by stellar populations yields numbers that exceed human comprehension. The observable universe contains more than 1 septillion stars. Written numerically, this figure requires 24 digits, 1 followed by 24 zeros. No human mind can truly grasp what this number represents. We can write it, speak it, perform calculations with it, but we cannot visualize 1 septillion of anything. Webb added another dimension to this census by detecting stellar populations that previous surveys missed entirely. Cool red dwarf stars constitute the most common stellar type in the universe. These dim suns burn hydrogen so slowly that they can shine for trillions of years, far longer than the current age of the universe. Their surfaces reach temperatures of only 2,000 to 3,000 degrees Kelvin, cool enough that they emit primarily in infrared wavelengths. Previous telescopes operating in visible light could not efficiently detect red dwarfs except in the immediate solar neighborhood. But Webb's infrared sensitivity reveals red dwarfs throughout the cosmos. The telescope detects their thermal emission with unprecedented clarity. Red dwarfs outnumber brighter stars by factors of 10 or more. For every sun-like star in the universe, approximately 10 red dwarfs burn quietly in the darkness. Adding their contributions to stellar population estimates increases the total count throughout the observable universe. The septillion stars we count using visible light observations represents only a fraction of true stellar populations. The planet count follows similar revision upward. Exoplanet studies conducted over the past 3 decades suggest that most stars host planetary systems. The Kepler Space Telescope discovered thousands of planets orbiting other stars, revealing that planetary formation is a natural consequence of stellar birth rather than a rare accident. Planets appear wherever the conditions for their formation exist. Some planetary systems contain only a few worlds. Others harbour dozens of objects ranging from massive gas giants exceeding Jupiter's mass to rocky bodies smaller than Earth's moon. The diversity of planetary architectures exceeds anything astronomers expected before systematic surveys began. Conservative estimates suggest at least 1 planet per star on average across the universe. This yields more than 1 septillion planets in the observable universe. The actual figure is likely several times higher, given the abundance of multi-planet systems and the detection biases that cause current surveys to miss small and distant worlds. The cosmos contains more planets than any previous generation imagined possible. Among these countless worlds, Webb has begun identifying candidates with potentially habitable conditions. The telescope's spectroscopic capabilities allow atmospheric analysis of exoplanets when they transit their host stars. During a transit, a planet passes between its star and Earth from our perspective. A small fraction of starlight filters through the planet's atmosphere before reaching our telescopes. This light carries absorption signatures from atmospheric gases. Different molecules absorb light at characteristic wavelengths. Water vapor absorbs at specific infrared frequencies. Carbon dioxide absorbs at others. Methane, ammonia, oxygen. Each atmospheric constituent leaves its fingerprint in the transmitted starlight. By analyzing these absorption patterns, astronomers can determine what gases exist in exoplanet atmospheres without ever visiting these distant worlds. Webb has detected water vapor, carbon dioxide, sulfur dioxide, and other molecules in exoplanet atmospheres. These observations provide direct evidence of chemical conditions on worlds dozens of light years distant. The telescope can distinguish between different atmospheric compositions, identifying which planets have thick hydrogen envelopes versus thin rocky atmospheres. The exoplanet K218b provided particularly intriguing results that captured global attention. This world orbits within its star's habitable zone, the range of distances where temperatures might allow liquid water on planetary surfaces. The planet is larger than Earth, but smaller than Neptune, a size category called sub-Neptune that has no equivalent in our solar system. Webb spectroscopy detected carbon-bearing molecules in K218b's atmosphere. More provocatively, The observations showed possible signs of dimethyl sulfide, a compound produced primarily by biological processes on Earth. Marine organisms generate dimethyl sulfide as a metabolic byproduct. Detection of this molecule on another world would constitute potential evidence for life. Alternative non-biological explanations exist for the spectral features Webb detected. Volcanic processes and photochemical reactions might produce similar compounds without any biological involvement. The observations require confirmation through additional analysis and future observations. Scientists remain appropriately cautious about interpreting potential biosignatures, but the detection demonstrates Webb's capability to identify potential signs of life on worlds dozens of light-years distant. The telescope can search for specific molecules associated with biological activity. It can characterize atmospheric compositions with precision sufficient to distinguish between inhabited and lifeless worlds, at least in principle. The search for extraterrestrial life has transformed from philosophical speculation into active scientific investigation. Scaling these observations across the septillions of planets Webb has helped enumerate suggests staggering possibilities. If even a tiny fraction of rocky planets in habitable zones develop conditions suitable for life, billions of potentially inhabited worlds exist within the observable universe. The cosmos might teem with biological activity, life emerging wherever conditions permit across the vast reaches of cosmic space. Whether life actually emerges under suitable conditions remains unknown. We have precisely one example of life arising from non-living chemistry: the origin of life on Earth, approximately 4 billion years ago. We do not understand this process well enough to estimate its probability. Or it might represent a fantastically improbable accident that occurred once in cosmic history. Webb cannot answer this question directly. The telescope can identify where habitable conditions exist. It can search for atmospheric signatures consistent with biological activity, but confirming the presence of life requires evidence beyond current capabilities. The question remains open, while Webb provides ever more precise constraints on where the answer might be found. The implications extend beyond mere counting of potentially habitable worlds. Understanding how common life-supporting conditions are requires understanding how planetary systems form and evolve. Webb observations of protoplanetary disks revealed unexpected complexity that shapes our understanding of planetary formation. Protoplanetary disks are the rotating clouds of gas and dust that surround young stars during the first few million years of stellar life. Within these disks, solid particles collide and stick together, gradually building larger objects. Pebbles become boulders, boulders become planetesimals, planetesimals become planetary embryos. The process continues until full-size planets emerge from the primordial disk material. Webb observed dozens of protoplanetary disks around young stars in nearby star-forming regions. The telescope's infrared sensitivity revealed chemical compositions and temperature structures invisible to previous instruments. The observations showed chemical gradients across disk radii, variations in molecular abundances that change with distance from the central star. These gradients determine what materials are available for planet formation at different orbital distances. Close to the star, temperatures are high enough that volatile compounds remain gaseous. Only refractory materials like silicates and metals can condense into solid form. Planets forming in these hot inner regions become rocky worlds like Mercury, Venus, Earth, and Mars. Further from the star, temperatures drop below freezing points for various compounds. Water ice condenses beyond what astronomers call the snow line. Carbon dioxide ice forms at greater distances still. Methane and ammonia freeze in the coldest outer regions. The locations of these snow lines determine what materials planetary embryos can accumulate. Webb observations revealed that snowline locations vary dramatically between different protoplanetary disks. Some disks show water ice forming much closer to the central star than theory predicted. Others show ice lines at unexpectedly large distances. The variations depend on disk mass, stellar luminosity, and disk structure in ways that complicate simple models of planetary formation. These discoveries connect to the cosmic web revelations through galactic environment effects. Galaxies embedded in dense filaments experience different evolutionary pressures than isolated systems. The local radiation environment affects disk chemistry and snowline locations. Star formation rates vary with galactic position within the cosmic web. The cosmic architecture, revealed by Webb, directly influences where habitable planets might concentrate. Planets forming in metal-rich environments have access to more heavy elements for building rocky cores. Planets forming in dense stellar environments might experience more frequent gravitational perturbations that could either enhance or disrupt the formation of stable planetary systems. The connections between cosmic web structure and planetary habitability are only beginning to be explored. Webb has also challenged assumptions about the cosmic timeline itself. Standard models estimated the age of the universe at 13.8 billion years. This figure derives from observations of the cosmic microwave background radiation combined with measurements of cosmic expansion rates. The age estimate has remained stable for over a decade, seemingly secure against revision. But the impossibly ancient galaxies Webb detected strain this timeline in ways that may require fundamental reassessment. Objects appearing fully formed at 400 million years after the Big Bang leave insufficient time for the evolutionary processes models require. Galaxies cannot assemble billions of stars in mere hundreds of millions of years, using the mechanisms our physics describes. Yet Webb shows that they did exactly that. Some researchers have proposed that the universe might be older than current estimates allow. The age calculation depends on assumptions about how cosmic expansion proceeded throughout cosmic history. If expansion rates differed in the past from what models assume, the light travel time from ancient galaxies might exceed 13 billion years without contradicting their apparent properties. Modified expansion histories could push the Big Bang further back in time. Perhaps the universe is 15 billion years old rather than 13.8 billion. Perhaps it is older still. Additional cosmic development time would provide more opportunity for structure formation, potentially resolving the tension between observed ancient galaxies and theoretical predictions. Alternative approaches suggest that time itself might operate differently at cosmic scales or during cosmic epochs. General relativity allows space-time geometry to vary depending on mass-energy distributions. The early universe contained matter at far higher densities than the modern cosmos. This extreme matter concentration would have affected space-time geometry in ways that might influence the relationship between cosmic expansion and elapsed time. If the early universe possessed different geometric properties than the modern cosmos, clocks would have ticked at different rates relative to the expansion of space. What appears as 400 million years of cosmic evolution, when measured by expansion, might represent longer periods when measured by the physical processes actually occurring. Stars might have had more time to evolve than the simple light travel time calculation suggests. These speculations remain theoretical. Webb observations motivate the questions, but cannot alone answer them. The telescope reveals what exists without explaining how existence came to be structured this way. But the pressure that Webb's discoveries place on standard cosmology ensures that creative theoretical responses will continue emerging. Something in our understanding is wrong, and finding what requires exploring possibilities that seemed unnecessary before Webb showed us the ancient universe. The revision extends to fundamental physics in ways that probe the deepest mysteries of cosmic existence. Dark energy, the mysterious force driving, accelerating cosmic expansion, comprises approximately 68% of cosmic contents according to standard models. This invisible energy permeates all of space, pushing the universe apart at ever-increasing rates. Without dark energy, cosmic expansion would gradually slow as gravity pulled matter together. With dark energy, expansion accelerates, carrying distant galaxies away from us faster with each passing cosmic epoch. Dark matter constitutes another 27% of cosmic contents. This invisible matter provides the gravitational scaffolding where galaxies form and the cosmic web takes shape. Without dark matter, the structures Webb observes could not exist. Normal matter would not concentrate sufficiently to form galaxies within the available cosmic time. Normal matter that we can see, touch, and directly detect amounts to barely 5% of total reality. Stars, planets, gas clouds, dust, biological organisms, everything made from atoms and electrons constitutes a small minority of cosmic contents. The universe is made mostly of substances we cannot see and do not understand. Webb observations constrain the proportions of these cosmic components, but cannot explain what dark energy and dark matter actually are. The telescope confirms that dark matter exists in the amount standard models predict by mapping the cosmic web and measuring gravitational lensing. It confirms that dark energy drives expansion by observing distant supernovae and galaxy clustering patterns. But confirmation is not explanation. The cosmic web architecture Webb revealed depends sensitively on dark matter properties. Filament structures would differ if dark matter interacted through additional forces beyond gravity. Supernova populations would change if dark matter particles possessed different masses. The excellent match between Webb observations and cold dark matter simulations strengthens constraints on what dark matter can and cannot be. Yet the fundamental identity of this dominant cosmic component remains unknown. Dark energy presents even deeper mysteries that Webb observations cannot resolve. Current observations remain consistent with a cosmological constant, an unchanging energy density inherent to space itself. Einstein introduced this concept in 1917, then later rejected it as his greatest blunder. Modern observations have restored the cosmological constant to central importance in cosmology, but theoretical puzzles surrounding the cosmological constant suggest that our understanding remains fundamentally incomplete. Quantum field theory predicts that empty space should contain enormous energy density from virtual particle fluctuations. The predicted value exceeds the observed cosmological constant by roughly 120 orders of magnitude, the largest discrepancy between theory and observation in all of physics. Either our quantum field theory calculations are wrong in some fundamental way, or some unknown mechanism cancels most of this vacuum energy, while leaving the tiny remainder that drives cosmic acceleration. Neither option is satisfying. Webb cannot resolve this puzzle, but its observations constrain any solution that theorists might propose. The scale revelations Webb provides affect humanity's cosmic self-assessment in profound ways. Previous generations might be forgiven for believing Earth occupied a special cosmic position. Ancient cosmology placed our world at the center of creation. The sun, moon, planets, and stars revolved around Earth in crystalline spheres. Humanity occupied the privileged position at the heart of existence. Copernicus displaced Earth from cosmic center by recognizing that our world orbits the sun rather than vice versa. But the sun might have seemed special, a unique stellar fire around which planets gather. Later observations revealed our sun as one ordinary star among billions in the Milky Way galaxy. But our galaxy might have seemed special, an island universe containing all existence. Hubble revealed our galaxy as one among many, scattered through cosmic space like islands in an infinite ocean. The number seemed large but comprehensible. Billions of galaxies, each containing billions of stars. The numbers strained human intuition but remained within conceptual grasp. Webb has demonstrated that the observable universe extends far beyond what previous instruments detected. Trillions of galaxies populate cosmic space. Septillions of stars burn through nuclear fusion. Countless planets orbit these suns under conditions that might support life. This scale transformation places human existence in unprecedented context. Every person who has ever lived occupies one small planet. Every civilization that has risen and fallen occupies that same small planet. Every thought that has occurred in any conscious mind throughout human history occurred on that one world orbiting one ordinary star in one typical galaxy, floating within one filament of a cosmic web, extending toward infinity. Some find this perspective crushing. The vastness revealed by Webb might seem to render human existence meaningless, an infinitesimal flicker in an uncaring cosmos that neither knows nor cares that we exist. What significance can individual lives hold when the universe operates on scales that dwarf not just human lifespans, but the entire duration of our species' existence? The cosmos existed for billions of years before humans evolved, and will continue for billions more after we are gone. Yet alternative interpretations find meaning precisely in this cosmic context. The same universe that stretches toward infinity in space and time, produced through processes we are beginning to understand. Conscious minds capable of contemplating their cosmic situation. This represents something remarkable regardless of scale. Matter organized itself over 13 billion years into configurations that can perceive, question, and investigate their own origins. Carbon atoms forged in ancient stellar cores assembled into molecules that replicate themselves. Simple replicators evolved into complex organisms. Complex organisms developed nervous systems. Nervous systems achieved consciousness. Consciousness developed curiosity about its own existence. This represents a transformation as remarkable as any that Webb has revealed. The universe began as a nearly uniform soup of hydrogen and helium. Through gravity and nuclear physics, that simple beginning produced galaxies, stars, planets, oceans, cells, brains, and minds. The cosmic story is not just one of expansion and structure formation. It is a story of matter becoming capable of contemplating matter. The telescope itself embodies this transformation in physical form. Webb is matter that has organized to observe other matter across cosmic distances. Its components derive from elements forged in stellar furnaces billions of years ago. Carbon in its structural materials came from red giant stars. Gold on its mirrors came from neutron star collisions. Silicon in its electronics came from supernova explosions. These stellar products were scattered through space, incorporated into molecular clouds, condensed into planetary systems, and eventually extracted by intelligent beings who fashioned them into instruments of cosmic observation. The ancient photons Webb collects travelled for billions of years before encountering mirrors made from atoms of similar antiquity. The observation process connects cosmic epochs through the physical substances that make it possible. The images Webb produces propagate through networks of electronic systems back to observing minds that interpret patterns in data as revelations about cosmic structure. Human consciousness processes the information, recognizes its significance, communicates findings to other minds. The loop connecting observer and observed represents something new in cosmic history. For most of cosmic time, the universe expanded and evolved without any awareness of its own existence. Stars burned and died without any process, registering their light as information. Galaxies formed and merged without any mind contemplating their structure. Dark matter collapsed into filaments and halos in complete absence of any knowing. Then, on at least one small planet, chemistry achieved complexity sufficient for self-replication. Evolution gradually refined this chemistry into organisms of increasing sophistication. Nervous systems emerged that allowed environmental response. Brains developed that permitted learning and memory. Eventually, consciousness arose that enabled reflection about existence itself. This cosmic awakening represents an ongoing process rather than a completed event. Webb constitutes the current frontier of the universe's developing self-knowledge, the cosmos examining itself through instruments of extraordinary capability, asking questions about its own history and structure that could not have been formulated until the very moment in cosmic time when minds and telescopes converged. The revelations Webb provides are not just discoveries about external cosmic reality. They are milestones in the universe's self-understanding. Each ancient galaxy Webb detects represents information the cosmos has gained about its own past. Each structural analysis revealing dark matter distribution constitutes understanding that the universe has achieved about its own organization. Through human investigation, the universe learns about itself. This perspective transforms cosmic vastness from something that diminishes human significance into something that contextualizes an extraordinary achievement. We exist in a universe capable of knowing itself through us. The scales Webb reveals are the scales of our origin, the reaches of space and time from which the elements in our bodies emerged, the history through which the processes producing consciousness unfolded. James Webb Space Telescope has shown humanity a universe larger, older, and more complex than we previously understood. The cosmic dawn reveals furious stellar activity when the universe was barely beginning. Dark matter filaments trace an invisible architecture that shapes all visible structure. Trillions of galaxies harbour septillions of stars, around which countless planets orbit through conditions that might permit life. This universe exceeds human comprehension while remaining subject to human investigation. We cannot hold cosmic scales in our minds, but we can represent them through mathematics and measurement. We cannot experience billion-year timescales, but we can reconstruct cosmic history through observations that capture ancient light. We cannot travel to distant galaxies, but we can understand their properties through the radiation they emit across cosmic distances. The true scale of the universe that Webb has exposed is not merely spatial or temporal. It is the scale of possibility. The range of what exists and might exist throughout cosmic space and time, from quantum fluctuations in the first instance after the Big Bang to the largest structures in the cosmic web, from the first stars that ignited during cosmic dawn to the future evolution driven by dark energy expansion. The universe encompasses possibilities that stretch toward infinity in every direction human inquiry can reach. We live at a moment when these possibilities are becoming knowable. Webb has opened windows that will remain open for decades as the telescope continues observing. Each new image reveals additional cosmic structure. Each spectrum constrains physical models. Each survey extends the census of cosmic contents. The universe that future generations will understand will be larger and stranger still than the one Webb is currently revealing. This ongoing revelation represents humanity's most ambitious collective project extending across generations. Thousands of scientists contributed to Webb's construction. Millions of people supported the institutions that made the telescope possible. Billions will eventually learn from its discoveries. The knowledge Webb provides belongs to no nation or group, but to the species that built it and the minds that will interpret its findings. What Webb has exposed is not merely the true scale of the universe. It is the true scale of human capability. We are beings who can construct instruments to see across billions of light years. We can formulate questions about cosmic origins and structures that the universe itself could not ask before conscious minds existed to ask them. We can create understanding where none previously existed. The universe that James Webb Space Telescope reveals will continue challenging every assumption we bring to its observation. It will force revisions in physical models as ancient galaxies continue defying expectations. It will alter cosmic timelines as new observations constrain when structures formed. It will shift philosophical perspectives as the scale of existence becomes increasingly clear. But through it all, the act of observation itself remains the most remarkable cosmic fact. Matter has organized to observe matter across distances measured in billions of light years. Chemistry has achieved consciousness capable of contemplating cosmic history. Life has developed curiosity about its own origins in stellar furnaces and planetary formation, and curiosity has built James Webb Space Telescope to reveal the true scale of the universe from which curiosity emerged. The cosmos is vast beyond comprehension. Its structures extend across scales that dwarf human experience by factors that language struggles to express. Its history stretches back through epochs, when nothing resembling current cosmic structures existed. And we are here to comprehend it, beings who exist for mere decades, contemplating a universe of billions of years, minds confined to one small planet, investigating structures spanning billions of light years. Consciousness that emerged yesterday in cosmic time, reconstructing the history of everything that came before. This is what James Webb Space Telescope has revealed. Not just the scale of the universe, but the scale of the achievement represented by observing it. The cosmos is vast, and we are here asking questions, building telescopes, seeking understanding. The universe has become capable of knowing itself. Webb shows us what that knowledge looks like when pushed to its current limits. The true scale is not just out there in the distant cosmos. It is here, in the act of looking, in the capacity to comprehend, in the remarkable fact that matter contemplates matter across the reaches of space and time. The cosmos is vast beyond comprehension, and we are here to comprehend it.